Alright, welcome to the first homework review of the semester. This is for Chapter 1, Homework 1, your very first assignment that was due yesterday. So we typically do pretty well on this assignment. I believe the average for this class, according to the quick Blackboard stats I looked at, was about 10.37 out of 12. So that was pretty good. And I'll compile later on today the total number of attempts that you guys did and see how that compares to previous semesters. But the performance overall is pretty good, and this first review will likely be kind of short because there's not too many problems to go over and they don't really have too many steps involved. So just in case you're not aware, the way that these work is I will go through the analysis in Blackboard of all the questions on the homework, and it tells me what percentage of people got them right. And I try to pick the ones that have the lowest success rate and give a few different categories of questions, so I'm not just doing the same thing over and over again, to try to go over some of the ones that seem to be the most difficult for you. As always, if you have requests for problems that you want me to cover in the review, please contact me ahead of time, by Sunday night ideally, or early Monday morning, and I'll be happy to include it. And always, if there's any questions that I don't go over that you're still stuck on, please come and see me sometime and we can go over those individually. Alright, so let's get right into it. The question that we had the most difficulty with was a conceptual question about the Rutherford Experiment. So, if you remember the Rutherford Experiment, he, as it describes here, he bombarded gold foil with alpha particles. So alpha particles are positively charged. And so essentially what he did was, I'll try to draw a quick sketch of it. He had a thin piece of gold foil, and then he sent a bunch of alpha particles towards it, which are positively charged. And he wanted to observe then what would happen to these alpha particles. Would they go straight through? Would they deflect? His hypothesis was that they would mostly go straight through, but that ended up not being the case. So remember what happened in this experiment was that you have most of the particles going straight through. I'll do this in a different color actually to show them going through. So most of the particles went straight through, but some of them got deflected even at pretty steep angles, almost going straight back in some cases. So there was a variety of results that were observed, as sort of a statistical distribution, if you will, but it was counter to the working hypothesis, and it led to some important conclusions. So the important thing is, this was the setup of the experiment, which is described in this problem. Now, what are the conclusions in this? Basically, all positive charge is in the nucleus. Nucleus is very small and dense, so it's a very tiny region of space where all that positive charge is localized. And then atom is mostly empty space. So these are kind of the key conclusions of the Rutherford experiment. And our job in this problem was to pick which of these 5 statements is not accounted for by the model he proposed. Alright, so choice A, the small size of the nucleus, that's pretty much the most obvious conclusion of this, so that's going to be included in the Rutherford model. The charge on the nucleus, and then C is the total mass of the atom. Now, this experiment did not actually directly measure the mass of the atom. It said that the mass of the atom is all located in the nucleus, but did not say what that mass was or how or any sort of quantitative measurement of the mass. So this one is going to be one that was not accounted for by the model. So that's likely our correct answer. But let's look at the other two. So a lot of times on these conceptual questions, you have no choice but to just go through all the choices, think about them, try to rule out the obvious ones, and then circle back to one. So we think that this one is not accounted for by the model. Let's see if any of the other ones work. D is the existence of protons. So his model did say that there were positively charged protons in the nucleus. The previous models also said that, but his said a little bit more about the in the location of those protons. And then finally, the one that I think most of you ended up picking was E, the presence of electrons outside the nucleus. And many of you picked this as the correct answer. Now, I think you were on the right track when you picked this answer, but we have to think about it a little bit more deeply, which is that even though the Rutherford experiment did not directly detect electrons, so his alpha particles They might be slightly influenced by electrons, but that wasn't really the main consideration of this experiment. But the point is, the model that he proposed, which was the nuclear model of the atom, still included electrons. So the Rutherford model, remember what we're looking for here is something that's not accounted for by the model, not necessarily that was directly measured in the experiment. His model still included electrons. So remember, the Rutherford model is basically that you have a tiny nucleus, and then you have this sort of diffuse cloud of electrons around it. So Rutherford still believed in the existence of electrons. Those had been proven before, and he didn't discredit that in any respect. His experiment directly interrogated the nucleus, but the model that he proposed still included the electrons floating around that nucleus. So the correct answer then is going to be choice C. All the rest, A, B, D, and E, were either directly came out of the Rutherford experiment, or at least were a part of the model that he proposed to account for his observations. All right, so that was the first one we had a little bit of difficulty with. Again, the Rutherford experiment being a very important one because it was the one that demonstrated that there is a nucleus. All right, another type of question we had a little bit of difficulty with is what is the sum of the numbers of neutrons and electrons in the ion 73 arsenic 3 plus, As3 plus being the symbol here, which is arsenic. So let's write that out. And we have to remember when we do this that this is the mass number, which we abbreviated as A. And then the one on the right side is the charge. So that would indicate that we have either extra or deficient in electrons. And then this is the symbol, which tells us what element we're talking about. All right, so I think for these types of problems, the best way to do it is sort of go through each subatomic particle individually. Usually you'll have to find at least two of the three in these types of problems. And so if we look at number of protons, that comes from the atomic number Z. Now Z is not given here. Usually Z would be in the lower left if it was included. As we said though, it's not often included in atomic symbols, so we need to go to the periodic table to figure out what is the atomic number for arsenic, which would tell us how many protons it has. So if you're not given the atomic number Z, but you are given the symbol as we are here, we just have to find that symbol in the periodic table. So arsenic is right here, number 33. It's one of the ones you should be very familiar with. We have the symbol, so you just have to find it here. So arsenic is number 33, and that number 33 that's above that symbol there, let me zoom in a little bit in case you're having trouble seeing that. So we find number 33, which is right here. Eventually it'll come into focus, I think. But even if it doesn't, we should be able to read that that's atomic number 33, which is telling us how many protons there are. So the number of protons, Z, is going to be 33. Now that's not actually being asked here, though. We're looking for neutrons and electrons, so we don't need that, but we actually need this to get the next couple answers. So then for neutrons, remember that the number of protons plus the number of neutrons equals the mass number A. So here what we have is 33 is the number of protons, number of neutrons we don't know, but then the mass number has to be given in any of these sort of isotope symbols, and that's going to be 73. So that means the number of neutrons is 40. Alright, so we're going to need that number because we're looking for the sum of neutrons and electrons. And then finally for electrons, remember that in a neutral atom the number of electrons is going to be equal to the number of protons. So we have 33 protons in this. However, we have a plus 3 charge. So if we have a plus 3 charge, we have 3 fewer electrons. We have extra positive charges. So the number of electrons in this case is going to be 30 because we have 33 protons, 3 fewer electrons to give us a plus 3 charge. So that means the number of neutrons plus the number of electrons, which is what this problem is asking for, is just going to be 40 plus 30 or 70. Now keep in mind that this problem is one of those ones that has variable input, so the value we could have given you for mass number and charge could have been different combinations for different versions of the homework, but the concept is the same. We use all three of these parameters, the atomic number Z, the mass number A, and the charge. All three of those go into solving this problem. So this one is a pretty nice inclusive example that gave us really insight into all of the different features of the atomic symbols. Alright, for the next one, determine the total number of electrons present in the atom, molecular, ion below and enter it as a whole number. And I forgot to enter the atom, molecular, ion in this file here, but the one that they were looking for in this problem was CH3+. Now this one we probably jumped the gun a little bit. We haven't really talked about chemical formulas yet, so a lot of people had some confusion on this, and that's okay. This one will make more sense in just a couple of weeks or so from now when we talk about chemical formulas. But the idea here is that you have, this is an atomic symbol. When you have a chemical formula, it's going to have more than one element in it. You're going to list the symbols in sort of in a row with each other, and then this tells you how many hydrogens there are. So if you have a number after the symbol as a subscript, that tells you how many of that atom are in the formula, how many of that contribute. So what we have in this CH3 plus, and then the plus is going to be a positive charge that modifies the entire ion. So this is, for the charge for the entire ion will be given up here. This is what's called a polyatomic ion. We're going to learn about those very soon. It's a collection of atoms that are bonded to each other, but that collection of atoms has an overall charge. Alright, so let's look at this one then. What we need in this case is we're looking for the total number of electrons. So we have one carbon atom in the formula. If there's no number next to it, that means you have one of them. We have 3 hydrogens, because this little 3 here tells us that there's 3 of those. And then we have one positive charge, which is going to also influence the number of electrons. So now what we need to do is just figure out how many electrons does each of these atoms have, and then what do we do with that positive charge. So for carbon, we have to go again to the periodic table, C, to find that symbol and figure out how many electrons it has. So C is up here. It's number 6. It has 6 protons, and then as a neutral atom, we would count also 6 electrons. So that carbon is going to contribute 6 electrons. We have one carbon contributing 6 electrons. Hydrogen, we have 3 of them, and if we go to the periodic table, this one we shouldn't need to look at, but if we forgot, hydrogen is the very first element here, number 1, so each hydrogen would contribute 1 electron. So we have 3 more electrons from hydrogen, and then finally we have the positive charge means we have to subtract 1 electron. Alright, because if we have a positive charge, that means we have 1 fewer electrons. So 6 plus 3 minus 1 gives us 8 electrons. We would just enter the number 8 in the blackboard. Alright, so that takes care of that one. It's a little bit more involved than we probably should have given you. This is occasionally going to happen. We're just trying to, stretch your knowledge a little bit. But like I said, we'll cover some of these things in more detail in the near future, and this will make a lot more sense. Alright, and then this last one here that has to deal with counting subatomic particles, specifically electrons in this case, kind of working backwards. We want to know the identity of element E if the ion E plus contains 18 electrons. Alright, so here we have to kind of think about things a little bit backwards. So E plus has 18 electrons. Which means then that E by itself, as a neutral, would have 17. I messed that up already. Would have 17. Sorry, I'm messing this up. 19. Now I can count today. It's still Monday morning. E would have 19 protons. Because if E plus has 18 electrons, that means E has to have 1 more proton than that. Or E as a neutral element would have 19. Another way to think about this is that if E plus has 18 electrons, and you'd add 1 electron to get to neutral, which would then tell you have 19 protons, 19 electrons in the element E when it's neutral. Anyway, there's a few different ways to think about that, but that's just, we come to the conclusion that we need 19 protons for E, so that means that our atomic number Z is going to be equal to 19, and now we have to work backwards and go to the periodic table and find which one has 19. So we go to find number 19, it's right here. So K, which is potassium, has 19 protons, which means that K plus would have 18 electrons. So the element would be K, we would enter that into Blackboard. Alright, so working backwards again, a little bit different than before, but same concept. If we have 18 electrons and a positive charge, that means we have 1 more proton than that. And then once we know the number of protons, we can identify the element from the periodic table. Because all of those atomic numbers, those whole numbers that are given on the periodic table, all of those indicate that we have that tells us how many protons there are in the nucleus, which is then representative for that element. All right, I think we just have one more here. Yeah, this last one. According to the law of multiple proportions, so this was again one of the three mass laws we covered. Definitely the most difficult conceptually for us to go over. All right, sorry, I keep getting distracted. I have to pause. All right, we're back. So law of multiple proportions. So this was the one that was, again, the most involved with the mass laws, and really the key element with law of multiple proportions, sort of the starting point to look for, is law of multiple proportions deals with, so again, there's more to it than this, but what we really want to zone in on when you're trying to answer a conceptual question about multiple proportions is the idea that we're talking about two, or sometimes more than two, but usually just two, but two or more different compounds, but they have the same elements in them. So if they're different compounds but they have the same elements, that means they must have different mass percent, or what we sometimes call mass ratios of the elements. That's what makes them different compounds from each other. So they have the same elements, but the elements are present in different ratios. That's what distinguishes the compounds from one another. And then finally, the last thing is then, this is the part that's a little bit more quantitative or mathematic, which is that, let's see the best way to think about this. So if you have, so let's say the elements are just generically A and B. The ratio of A to B in compound 1 Alright, so the idea here is that we have these mass ratios of the two elements A to B, and that ratio of A to B by mass in compound 1 and A to B by compound 2, those two ratios are different from each other, but they're related by simple fraction, small fraction, or whole number. So as an example, just random example here to sort of illustrate this more concretely, if the ratio of elements A to B in compound 1, let's say it's 1.5, so that means the mass of A over the mass of B is 1.5. That's just a random example. If you have the second compound that has those same elements, compound 2 as I'm calling it, A to B could be equal to a lot of different things, but it's going to be something that's a simple multiple of this. It's something like 3 or 4.5, which is 3 times 1.5, or maybe, like, at worst, it'd be 1.5 times 1.5, which is like 2.25. So in other words, these two mass ratios for the two compounds are related to each other in a very simple way, either twice or 3 times each other, or maybe 1.5 times each other, but very simple relationships between the mass ratios. So again, that's kind of an involved one to really understand all the details of, but let's look then at the answer choices, where we're just trying to figure out which of these 4 statements is given by the law of multiple proportions. So statement A, if the same two elements form two different compounds, so that is sort of the setup point for multiple proportions, they do so in the same ratio. So this is the part that's wrong. Remember that if we have same two elements forming two different compounds, they have to be different ratios. So that should be different ratios. So that statement is false, as written. Choice B, it is not possible for the same two elements to form more than one compound. Again, this is sort of the basic essence of multiple proportions, which states that it is possible. So this one is also wrong. It is certainly possible for the same two elements to form more than one compound. The example in our everyday lives that we're probably familiar with is carbon monoxide and carbon dioxide, which are two different ratios of carbon and oxygen. We also know water and hydrogen peroxide are both made up of hydrogen and oxygen. I give an example in class of different compounds with iron and oxygen. So there's a lot of examples where you have the same two elements, but they form more than one compound. So that's definitely false. Choice C, the ratio of the masses of the elements in a compound is always the same. This is a true statement, but this is actually not part of multiple proportions. This one is part of the law of definite composition. So this is a statement of one of the other mass laws here, definite composition, which deals with the mass ratios of elements in a single compound. Now this is in some sense part of the multiple proportions. In other words, the law of multiple proportions kind of follows from the law of definite composition, but this by itself, choice C by itself, would just be the law of definite composition, not the law of multiple proportions. So that one's wrong, not because it's false, but because it's part of a different mass law. And then choice D, the total mass of a chemical change is the same as before the change. So this is actually a statement of the law of conservation of mass. So again, this is a true statement, but it's the wrong mass law that we're talking about here. So that's also not part of law of multiple proportions, which leaves E, none of these. Now I realize that there's a psychological barrier to picking none of the above as the correct answer, but that will happen sometimes, and it did happen here. And so really the key point is to look at all four of these answer choices. You both need to know which of these statements are true. So A and B are not true at all, C and D are true, but then you also need to know of the true statements which of those are part of law of multiple proportions, and neither of these last two statements are. So kind of, again, a couple of layers to the onion on this one, but really understanding the concept of multiple proportions is what we expect you to be able to do. We're not going to have a lot of detailed mathematical questions dealing with multiple proportions, but we want you to know sort of the basic elements of it. All right, so that takes us to the end of this first review. If there's anything that I did not cover in sufficient detail for your liking, of course let me know, and I'd be happy to go over it some more with you individually. I hope you find these useful, and we'll have one of these every week, so enjoy the first one.